Okay, so this talk is actually, we saw yesterday then in the introduction, a large fraction of the participants to this coding theory workshop are not coding theorists, and proudly so. So I will actually, I don't know how to classify myself, but I will actually, I think that it's a good idea to spend 10 minutes, since this is the first talk, doing some coding theory, right? And so I'll talk about, give a crash course into the part of coding theory that I find most interesting, that is codes on graph and probabilistic decoding, just at high level. And then what I'll try to do is that I'll try to put these things in a broader context by describing basically a short list of problems. The list might be much longer, in which very similar things seem to pop up. Okay? So people that know about coding theorists might say, haha, about this part might say, haha, this is the same as coding. Okay? And yeah, so two disclaimers. I will not state formal theorems. You can ask for them if you want, but in the interest of time, I'll try to be very synthetic, and so not go into many detail. And of course, I'll give a few examples, and please interrupt me. So this is the more detailed outline, and the three examples are basically chosen because they are easily connected to the first part. So codes on graph. Okay, so this is the picture. You want to send bits to a noisy channel, and say that the model is that each observation is the original bit plus a Bernoulli random variable with bias p. And LDPC codes, the way they work is that you don't send any sequence of bits, but only those that satisfy a set of parity checks. That here I represent as a graph, and each of these nodes means that the mod 2 sum of the variables here have to be 0, and only those words that satisfy these constraints are valid code words. Okay, and if you accept this as the code that you want to use, really what is the problem? The problem will be estimate the x size given observations, noisy observation y. Okay? So you want to use somehow the noisy observation and the structure. Okay, and of course, as we saw yesterday, there is 40 years, or 50 years history of analysis of these codes, and so I'll give the 2 slides summary of what is known, and I'll focus on what is known on, large block length. So I take such a graph, as block length to infinity. Now, how you construct such a graph? Basically, all the construction boil down to the following: take a random graph with some constraints. Okay? So now, of course, the devil is in the details, in particular on what constraint you want to put, and people came up with very smart way of imposing these constraints. The simplest that dated back to Gallagher is simply impose the degree to some given value, but people came up with much smarter ways that allowed to achieve capacity. Okay, so very nice and interesting graph ensembles to study. Okay, so what is the generic behavior? So this is a plot that refers to the simplest possible of this code, the rate 1/2 code with degree 3 on this side and 6 on that side. So this is rate 1/2, and what I plot here in x-axis is basically noise level, and the y-axis the performance. So 0 means 0 decoding error, and 1 means complete rubbish. And more precisely, 2 nice coordinates that is nice to use is to plot on the x-axis the entropy of the channel flip probability. This is nice because it's between 0 and 1 for any channel. And the y-axis something that is similar to entropy, and it has this form. You take your favorite algorithm. This will output soft decisions, that is estimates of the posterior probability of each bit I. So call this PI alg. you compute some function g of this. So think of this as entropy. It's not the entropy, but there's many properties of the entropy. It's increasing in particular, and it's between 0 and 1, and average this over all the bits. Okay? So this 0 means that you are decoding perfectly, and 1 you are getting complete rubbish. And this is the picture. If you apply, a local decoder that is belief propagation, this gives perfect decoding below a certain threshold, and then follows a certain curve above the threshold. So this is the threshold for that decoder. Now this figure instead refers to the ideal decoder. That is the decoder that computes this pi, returns this pi as the posterior probabilities. So pi will be the posterior probability that bit I is 1 given all the observations. Right? This is something that you cannot compute in general. You don't know how to compute in general, but you can analyze. And turns out that the threshold of this is related to the threshold of this algorithm by a very interesting and simple construction. You just look at this curve and find the vertical line where these two areas match. So you cut any vertical curve, cuts a slice here and slice here, and you find where the two areas match. So you get two thresholds. Both thresholds are below 0.5. Okay, so just sanity check why they are below 0.5. To see whether anybody is following.
Did you say which code you're using?
Yeah. 1/2 code. Okay. Somebody want to answer? It's too easy.
Is it the 3/6 code?
Yeah.
3/1/2.
So it's written 1/2. So 1/2 here is Shannon upper bound, so is Shannon capacity. Okay, so these are the generic features that I want to remember of this picture. Okay, there is phase transitions. There is a phase transition for local algorithms. In this case, it's belief propagation. So what I mean by this is an algorithm that for each vertex computes pi alg just by looking at the bounded depth neighborhood of vertex I in the graph for any bounded depth. And this has a certain phase transition. There is an information theoretic phase transition. This is the information phase transition of that code is at HMAP. And interestingly enough, despite probably, again, 60, 50 years of research, nobody knows any polynomial algorithm that works in this interval. And recent discovery is that you can take the graph and massage it a little bit through this spatial coupling technique in such a way that the BP threshold becomes equal to the map threshold, and this slice gets cut off completely. Okay. This is kind of magic the first time that you see, but that's true. Okay.
Sorry.
Yeah.
So spatial coupling is polynomial time, or
so spatial coupling.
Opposing statements, or
So spatial coupling is a modification of the graph. So you take your graph. So what I said is that the graph is random with some constraints. You can think of spatial coupling adding a little bit more constraints. It's interesting because the graph remains basically very similar to the original graph, and similar enough that all this part of the curve, for instance, remains the same. But it's not, it's different enough to slice away this curve. Okay, so it's kind of a magic, trick that take a problem that is NPR, then changes it into a problem that is solvable under local algorithm, and that has very similar properties. Okay, so this was the course in coding theory. And so now you're all coding theorists. And so I'll now do two examples in which similar things happen, surprisingly. One is compressed sensing. Okay, so here the model that I want to look at is the following. You have a vector x of length capital N, so it's a big vector. You hit it with a matrix, and the matrix is a random matrix, say a random matrix with IID normal 0, 1 over entry, and the matrix is known at the decoder. You observe y, so y is a times x plus some noise. What you observe is y and a, and you want to reconstruct x naught. Okay. So at a high level, looks very similar to the thing before. You have some unknown bits or some unknown variable. Here they are not bits. And you have some noisy observations. And now the problem is dense. This matrix is dense. There is no natural notion of locality. So what I want to replace for locality is a class of algorithms that takes this form. And we introduced it in this paper. One way to see them is, as a limit for dense graph of the algorithms of belief propagation type. Okay? So this is what we call approximate message passing, and the way they work is basically they apply AA transpose and then they do some nonlinear operation. So at each iteration you take your current estimate, your current estimate, you subtract it from the observation, you construct the residual, and then you back project with A transpose, and then you do some nonlinear operation. There are many ways of deriving this. I will not go into detail. One way is, again, you take a problem on a sparse graph, take belief propagation for that problem, and then you formally take somehow a good approximation for the degree getting larger. Okay, and so now one interesting difference between this problem and the original problem that I want to retain and that is important is that in the coding problem you know the distribution of x naught because you know the code. The decoder knows the code, knows that whoever is transmitting is sampling a code word uniformly at random. In this problem you don't know the real distribution of x naught. Okay? So you can think of two cases, two limits cases. One is you know a prior, exactly. This is idealized and lower bound. And so at each step, in that case, the prescription is that here you want to do the MMSE denoiser for decoding. And the other extreme, you don't know the prior, but you know some feature of x naught, for instance, that is sparse. In that case, you want to use at each step the minimax denoiser for that class. That is basically the best denoiser for the worst distribution in that class. Okay, so these are examples. So what happens, the first discovery is that again there are phase transitions here. And here this is a figure from a paper in which we studied a bunch of different denoisers. So this is this nonlinearity. Takes different forms, but the basic concept is that if you see something that is close to 0, you set it to 0. If you see something that is different from 0, you try to leave it where it is. And what you see now, this is for sparse vectors, and what you see now is the following, that if you fix a sparsity level of your vector x naught, and now the equivalent of the SNR is the undersampling. So is the aspect ratio on this matrix. If you fix epsilon and move the undersampling, you undergo a phase transition, and this phase transition will depend on this nonlinearity. So below this point, the algorithm reconstruct basically doesn't reconstruct at all the original x naught, and above it reconstruct basically exactly.
This is for AMP.
Yeah. Yeah. So okay. Now there are connections between this, for instance, and doing convex optimization. In particular, if you take one of these denoisers, that is I think the blue one, that is soft thresholding, then this is the same phase transition as L1 minimization. There is a reason for that. Okay, so what is the big picture here? So, okay, you can do all of these analyses, etc. what is the one-line summary. There have been a lot of work in this area. These are only papers that are very, very related to what I'm talking about, some by people in this audience. But the one-line summary is that is the same as the picture that we saw in the case of LPPC codes. Okay, and this is one picture to show that. Okay. This is similar to what I had before. Okay. So I fix a level of sparsity, and now I trace two phase transitions. One is, the information theoretic phase transition. It's what you would do, where the phase transition sits, if you could, compute the base posterior of this model. Compute conditional expectation of x given vector y, of all the vector x given vector y. Surprise, surprise, this ideal algorithm that you cannot, it's non-polynomial algorithm, works as soon as delta is below 0.2. For epsilon 0.2 works as soon as delta is 0.2. This basically means that it works, it reconstruct x from as many observations as unknowns, plus small o of n. This is kind of, surprising. Then you look at what this local algorithm achieve if you just assume that you know the prior, but you force yourself to use local algorithms. So a certain class of polynomial time algorithm, you get a bit worse. This is, I don't remember what is the distribution here that we use. It's probably some Bernoulli. But you get a bit worse, quite a bit worse. And then this is what you get if you don't know the prior distribution, so there is an extra loss. Okay. So at high level, so the first line is somehow new because it's related to the fact that you don't know the distribution of x, but all the other lines are the same as before. So you have a phase transition for local algorithms, and this is this one, the blue one. You have a phase transition that is information theoretic. This is the red one. So this was actually first, information theoretically was proved that you can achieve it by Hyong and Sergio Verdun. In this interval, between the red and the blue, I don't know of any polynomial algorithm that does the compressed sensing reconstruction. But you can modify your sampling matrix, your sensing matrix, using the same trick of spatial coupling. This was first suggested by Kudekarp-Pfister and then by Florent and others. And then we proved it. And you can squeeze this phase transition to 0. So there are matrices such that you can hit the vector with that matrix and then reconstruct with a polynomial algorithm and do it from a number of observations that is the number of non-zeros plus small o of n. Yeah.
So the minimax refers to the sparsity level?
You know the sparsity level?
Do a max over the distribution
of
the x's on the non-zero support.
Okay. But you say it's minimax phase transition for local algorithms.
Yeah.
What about the best algorithm?
Good question. The best algorithm, if you don't put polynomial constraint, is this. If you put polynomiality constraint, then the question is really hard, right? If you can prove a lower bound for all polynomial algorithms.
But didn't you say it's bias? Like the diagonal?
What? The blue ones?
The dash diagonal, you said it's bias. It's not
That's the optimal thing. You do the base posterior. With respect to MMSE, this is the base. You do the base posterior. But this is not computationally effective. That is computing, for instance, E of x given y. E of vector x given the vector y. Okay.
You can explain further why they're the same picture? Or that's it?
That's it. So I don't have time, 5 minutes, to explain anything, right?
Thank you.
So I want to give you one more example because this is actually, so in this, okay, it's interesting. So if you are, a positive, a half, glass half full person, you say, okay, this is nice because, you can get pretty good reconstruction, etc. I'm a, glass half empty kind of person, and when I see this picture, I find very interesting this frustrating region in which you can do the reconstruction. Okay, so this is an example in which the frustrating region becomes huge. Okay, and let me again motivate it from coding theory, and I'll motivate it using, it's a kind of ad hoc motivation for this workshop. It's not really was our motivation, but using LDGM. So what is LDGM is, you have a vector of bits, and now you use this graph to compute parity bits. So you compute mod 2 sums of this bit, and this is what you send through the channel. And the graph is sparse. Okay, so what an LDGM does, for instance, fountain codes are a very nice example of LDGM, but here I'll take regular LDGMs. So each time I take 4 bits, and I take the mod 2 sum of those 4 bits, and I send it through the channel. So this gets added noise. Now, this you can write in 0-1 notation or in +-1 notation. So now the mod 2 sum becomes multiplication. So you take 4 +-1 signs, and you send it through the channel, other 4, and you send through the channel, etc. And each transmitted symbol is the combination of 4 information symbols. Okay. Now let me add another twist to this. In LDGM, normally you send a number of bits that is proportional to the number of unknown bits, but let me do a twist. I'll send a number of bits that is equal to n choose k. So if I take combinations of k bits, I'll send all the n choose k combinations through this noisy channel, and I'll add the Gaussian noise. So this is the model. For each couples, I send this k bits, I add Gaussian noise, and this is what I receive. Now this I can write in tensor notation. What I'm doing is that I'm taking a vector x and taking the outer product of it k times, add, multiply by coefficient and add Gaussian noise. Okay. So the real motivation why we studied this is that this is currently a topic that has attracted quite some interest in machine learning, how you do data analysis where your data form a tensor. And this is a very simple model for this. The model is the following. I have an unknown signal. I take the outer product of this signal with itself k times, and I add Gaussian noise. There is a simple, the case k equal to of this problem is something that has been studied in tens, dozens, or hundreds of papers in statistics. Is called the spiked model. And so this is a spiked tensor model.
Is this also your motivation for yesterday's open problem?
Sorry? Yeah. Well, yeah. The open problem is more general. Yeah. Okay. Now, what is the same? The big picture is very similar to LDPC codes, but now the gap is huge. Now, the only thing here, it doesn't make a lot of sense to talk of spatial coupling, of course. But what's interesting is the following in this problem. You can compute what is the information. We proved some simple upper and lower bounds of what is the information theoretic phase transition. So it's the phase transition if you do the optimal reconstruction. And this is a signal to noise ratio equal 1 if you scale things in the right way. So the right scaling is this. If you do the right scaling, then the SNR for the information theoretic phase transition is some constant. Okay. You can, it should have a sharp threshold. Now, if you try local algorithms, you get that this works when the SNR is bigger than basically n to the k over 2. And there is a slightly smarter thing than local algorithm that it's called matrix unfolding. And if you ask me a question, I will explain what it is. And this achieves n to the k over 4. And there is, this is, I think this is this should be between 1 and this, and to the 0. But there is no polynomial algorithm is known in this interval. Okay, so there is a diverging with the sides interval in which everything fails. Okay? So it's interesting that this is very different from the classical statistics case, that is k equal 2 is standard principal component analysis. In that case, there is no gap. There is a phase transition in which just computing the principal vector works, and below that, no algorithm can work. And this is called, sometimes the Bike-Benarus-Pesce phase transition.
What's the assumption on x? Did you assume this first? Or?
What the assumption?
X. Did you assume
X, no, norm 1.
I see.
Generally.
Right.
Yeah, here X is just norm 1. Okay, so these are one simulation.
So K equals 2 is just matrix PSDA, right? Just
Yeah.
just a standard PSDA.
Yeah, so that you just compute the principal eigenvector of the matrix, and this as the optimal threshold. That is, SNR equal 1. So this is how it works in simulation. This is a bunch of algorithms. These are all local algorithms, and this is all matrix unfolded based algorithm, and this is standard local algorithm, and this is. As n gets larger, everything fails eventually. Okay, I want to talk about planted CSP, but I think it's okay. And I think that there is this convergence between several teams that have been taking place for a few years, but the number of open problems that are interesting increase is at a faster pace than anybody is able to solve them. So.
So what is your matrix unfolding algorithm? You just string out the tensor as a matrix, sort of in half, n over 2, n over 2.
Yeah. So and
Then just do PCA on that.
and then if a k, you can think of doing it recursively.
Yeah. The other part.
Now, if you're interested in really reconstruction error, what you want to do is empirically, we don't have any theorem, you want to do that, and then on top of that, do some greedy optimization, for instance, power method or whatever you want. But if you're just interested in the threshold, what you said is as good as anything I could think of. And if you have any better.
Does recursively mean if you know how to solve a k-1 tensor, you use...
No. Recursively, what I mean, if you have a tensor of order 16, so you do it n by n to the 8 by n to the 8, and then you get a tensor of order 8. I mean, the solution is a tensor of order 8, and now n to the 4 by n to the 4. Now I get a tensor of order 4, etc. I mean, when I unfold the tensor, the solution that I get is, you have to it's good to get it, of same sides. The solution that you get is also a tensor of lower order.
So, in this tensor problem versus the coding theoretic problem that you map this tensor problem from, they're a little different, right? There you had M choose K different products, whereas here you have more data and in a specific additional structure.
Yeah.
So the upper bounds on the error for the tensor problem also carry over there?
No, I think that, okay, so I think that if you do the analysis in that case, you can get similar things, but you will not, if the graph is sparse, you will not get a diverging gap. You will get a gap that is order 1 and somehow depends on the degree of the graph. This is my guess. This is the same as you get in LDPC codes, but for LDGM codes, right? Yeah. So this is kind of, if you want to think of it as a code, it's a code in which you are sending a very small rate over a very noisy channel.
So, Andrea, I thought you said in the last problem you were discussing that spatial coupling didn't apply, or
No, it doesn't. Yeah, it's difficult to justify, right? In coding theory, you can justify very well because you can say, okay, I designed the metrics. In compressed sensing, you can justify so and so, right? Because you have some space for designing the sensing metrics, but you are very constrained from the system. Here is really our motivation was really machine learning. There you get so typically what people are interested in is stuff like you have data about users, products, and days of the year, right? This is a data set, right? So you cannot impose. Of course, you can, if you want to work on it, then you can probably, you know how to do it, right? It's like an LDGM, you do an LDGM, which is special.
I think we should wrap up unless you guys don't.